Let's talk about the rank of a matrix in this video. Its definition is as follows. The rank of a matrix A is the number of leading ones in any row echelon form of A. Notice that we have made an assumption here, which is that the number of leading ones in any row echelon form of a matrix is fixed. This is a non-trivial fact which needs to be proved. However, we will not present the proof here because we do not have the necessary knowledge to prove it at this point. So we will just assume it for now. Let us see an example of how we can compute the rank of a matrix. Say we want to compute the rank of this matrix A. By definition, it suffices to reduce A to row echelon form and count the number of leading ones. To start, we observe that the leading entry in the first row is 3, and the leading entry in the second row is 1. So we first swap the first row and the second row. So we obtain this matrix. Next, we subtract 3 times the first row from the second row and add the first row to the third row in order to create zeros below the leading one in the first row. The resulting matrix is this. Therefore, we just need to divide the third row by 4, and we obtain the row echelon form of A as follows. Now, it is easy to see that there are 3 leading ones in the row echelon form of A, which means that the rank of A is 3. Now, let's look at a theorem. Suppose a system of m equations in n unknowns is consistent, and the coefficient matrix A has rank R. Then we have the following results. The first one is that R is less than or equal to the minimum of m and n. Secondly, the set of solutions has exactly n minus r parameters. Thirdly, if R is less than n, then the system has infinitely many solutions. Lastly, if R equals n, then the system has a unique solution. Let's prove these results one by one. For the first point, since A has m rows and the leading ones lie in different rows, R is less than or equal to m. Similarly, since A has n columns and the leading ones lie in different columns, R is less than or equal to n. So R is less than or equal to both m and n, which means that it has to be less than or equal to the minimum of m and n. For the second result, since A has rank R, it means that there are exactly r leading variables in the system. Since there are n variables in total, and each variable is either a leading variable or a free variable, we know that there are exactly n minus r free variables. In other words, exactly n minus r parameters. For the third point, when r is less than n, there exists at least one parameter, which means that the system has infinitely many solutions. For the last point, since r equals n, we know that there are no parameters. In other words, there is a leading one in every column of A. And since the system is assumed to be consistent, A takes the following form. More precisely, the main diagonal entries are all leading ones, and the entries below them are all zeros, and the entries to the right of them are irrelevant, which are all denoted by star. Notice that the number of 0 rows in A is m minus n. It is clear now that by doing backward substitution, we can find a unique solution to the system, because whenever a value of an unknown is put into an equation, there is only one variable left in the equation, so its value can also be uniquely determined. There is an interesting corollary to the theorem, which is that there are only 3 cases for any system of linear equations. It can have no solution, a unique solution, or infinitely many solutions. That means that it is not possible for a system of linear equations to have exactly 2 solutions, exactly 3 solutions, and so on.